Welcome to my living room, i.e. your classroom for the next semester. First lecture, we're getting it recorded. I'm having fun with some gorillas. This is how we're gonna get down. All right. Hope you all had a good semester. I'm gonna try to keep this real fun during the first couple minutes of each lecture, all right? I also want to tell you I got this funky Michael Jackson half glove going on. It's for my tablet, my document writer, all right? So if you see this is normal. This is how I'm keeping it real. Okay, let's get it started. Okay, awesome. So what I have here are our lecture slides, all right? And I'm going to be filling in information as we go. So using this document pen writer is a little new for me, so I'm going to ask you to have a little bit of patience as I'm working through it, okay? With practice makes perfect, so hopefully I'll get better at writing at this thing as we go, all right? And so I'm going to take my time writing with this, so if you need to watch me in 1.5 speed, I'll never know, and that's totally cool. So let's get it going. So I want to talk about units. Units are going to make everything in this course. And if there's ever a time when we don't remember an equation, we don't remember how to solve a problem, the unit analysis has to work. Even through some complex integral or derivative, the unit analysis still has to work. Okay, so let's go through this. So let's remember a Newton, the SI, right, is a kilogram meter per second squared. Okay, so let's write that down. Let's see how this goes. Kilogram meter per second squared. Okay, so we recognize then that a joule is actually a Newton meter. It's a Newton times a meter, or work is force times distance, right? And units of work are energy. So thus we know that a joule is a kilogram meter squared per second squared, okay? We know a watt is a unit of power, joule per second, or we could say a kilogram meter squared per second cubed. So Pascal is a unit of pressure, which we could think of pounds per square inch, right? It's pressure is force divided by area, so that's pounds per square inch. But in our SI units, that's going to end up being, of course, a Newton per square meter. So because that's a Newton per square meter, that's going to make it a kilogram per meter second squared. Okay. So an amp, we're not going to quite get into so much electrochemistry, but it's still an important unit to talk about. So that's a rate of charge. So that is a coulomb per second. And of course, what's a coulomb? So I'm going to cheat here and just say a coulomb is an amp times second, right? You could do the algebra to see how that works. And a coulomb is a unit of charge, okay? So then now a volt, hopefully you remember from your electrochemistry days, is a joule per coulomb, or of course it's a joule per amp second. So we're not going to use volts as much as we're going to use electron volts. Electron volts will be one of our fundamental units of energy. Okay, it is a unit of energy, or it can be at least. So an electron volt is, of course, a joule per coulomb times fundamental constant E. And notice that I'm not talking about natural number E. This is the fundamental constant E, the charge of an electron. Okay, so that equals, so let's say 1 eV equals a joule per coulomb times, and that value of E, if you recall, that's 1.602 times 10 to the minus 19 coulomb, and so that can be plus or minus, right? An electron is negative 1.602 by 10 minus 19. Proton is positive that value. But all the same, you can see with the unit analysis, this means 1 electron volt is 1.602 times 10 to the minus 19 joules. Okay, and we're going to keep getting more and more into that electron volt unit because when we're talking about the energy of single electrons or single molecules, it's much easier to say 1 electron volt than 1.602 times 10 minus 19 joules. Okay. And so now last I want to talk about the wave number, and I want to talk about the spectroscopic wave number. Okay, so this gets a nu with a little tilde sign there. Okay, so it's going to be easy for us to call that a V, and I totally forgive you if you don't know all the Greek letters, but technically it's a nu with a little tilde. That's different than the frequency symbol, if you recall. Frequency is a nu, but it does not have that little tilde symbol. Okay, and the wave number is 1 over wavelength. So typically you might have seen wave number in your OCHEM FTIR as 1 over centimeters. And right, that's 1 over length. The SI is technically 1 over meters, right? Meters is the preferred SI units. And if you recall the equation, E equals HC over lambda, if the wave number is 1 over lambda, then that means we can convert any quantity of energy into a equivalent wave number by rearranging this algebraically, right? And so if I divide both sides by HC, then I recognize the wave number, which is 1 over lambda, or 1 over nu tilde, is just E over HC. Okay, and so what's useful then is to say, well, how many wave numbers is an electron volt? So go ahead and calculate that. I'm going to play some music while I am calculating that. Okay, and you can pause the video or follow along with me as I'm going to do these calculations throughout the lecture.
The revolution will be televised. And the pollution from the ocean, now with devotion. Push peace and keep it in motion. Kids gather around, yeah, I need your focus. I know it seems like the world is so hopeless. It's like Wonderland. Now fascinate me, picture and animate me, cause I'm rolling, heat holding, click clacking, crack-a-lacking, folk packing, mo stacking, acting a fool when I teach. Welcome to the world of the plastic beach. Yeah. Welcome to the world of the plastic beach. Mirror, mirror on the wall, boss dog, get it to 'em, get involved, turn it up, speed it up, slow it up. Underground, but he under us, undercut, shipped up, chipped out, swimming with the sharks with my gills up, turn the wheels up, real tough, drinking lemonade in the shade, getting blade with a gang of pilgrims. Yeah, this my path, belly flopping like while I'm rocking in the bubble bath. And I'm just like that, four zones added up to get you okay.
Okay. Okay, so I got 8,064 inverse centimeters, 8,064 wave numbers for 1 electron volt. And I'm not going to ask you to memorize stuff, but I think it's generally pretty nice to have an internal scale, if you will. What is 8,000 wave number? What is 1 electron volt? And so you can see, if you recall from your FTIR, from OCHEM, the highest energy that you probe is about 4,000 wave number, right? Remember that OH stretch is around 3,500 wave number, right? So 1 electron volt is outside of the IR, but it's close. It's right in that range. It's very close to the IR. Okay. So let's talk about the gas constant that you all know and love. So we have two flavors of the gas constant. Okay, we know 8.314 joule per mole K. Oops, that's gonna happen. I gotta get used to that. All right. So that's 8.314 joule per mole K. Oh, look, I got an undo button. Yes. Let's try again. 8.314. I don't know if this is any better, but I'm trying. Okay. So, and you know the other flavor as 0.08206 liter atmosphere mole K. All right. Let's write that down again. 0.08206 liters ATMs per mole Kelvin. Well, I also want to let you in on a little secret. The gas constant is a disguise for one of the most fundamental constants in the entire universe, which is Boltzmann's constant. So we talk about the value of Planck's constant, h, and the speed of light, c. Those are two very important constants that hopefully you're aware of that. Something you're probably not aware of, just how important it is Boltzmann's constant, okay? And the way I like to describe the gas constant and Boltzmann's constant is Bruce Wayne. The gas constant is Batman. Think about that. Think about that for a minute, okay? And watch, I'll show you something. So if I go 8.314 joules per mole per Kelvin, and I say in 1 mole, there's 6.022 times 10 to the 23 things. And we remember it doesn't matter what those things are. They could be molecules, atoms, electrons, chickens, whatever. It's a number. Okay? So if I go and carry out this operation, then I get 1.3806 times 10 to the minus 23. And I'm just going to write that as joule per Kelvin because that's technically joule per Kelvin per one singular thing. Joule per Kelvin per molecule, joule per Kelvin per atom, whatever you want. This is the Boltzmann's constant. Okay, so you see what I mean? You've known about Boltzmann's constant the entire time you've been a chemist. You've just thought of it as the gas constant. Okay, so that's why Boltzmann's constant is Bruce Wayne, gas constant is Batman. They're the same thing. We will primarily stick with Boltzmann's constant, but we can use the gas constant too if we're talking about per mole quantities. And this leads me directly into this final discussion here on this slide, extensive properties versus intensive properties. Okay, so an extensive property depends on the amount. An intensive property is independent of the amount. Okay, and so I want you to think of some examples for just a few minutes. What is an extensive property and what is an intensive property? Okay, so some of the examples, so as you're thinking, pause the video and think about this so that you can really get a nice handle on it. So I'll give you one example of an extensive property because it depends on the amount, and that's mass and volume, right? The mass of a quantity I have absolutely depends on how much of it I have. Similarly with the volume. Aha, but what about this intensive property that's independent of the mass? Well, what if I take mass divided by volume? We know that as density. Technically, density gets a Greek letter rho, okay? And density doesn't matter how much you have. The density of water at room temperature is the density of water at room temperature, whether you're talking about an ocean or a cloud droplet, right? Of course, that depends on what its composition is, without getting too complicated, right? The density of pure water is intensive. It's independent of the amount. So maybe you're even connecting a bigger picture there. If I take two extensive properties and ratio them, such as mass and volume, I now have an intensive property. Okay, so we're going to be thinking a lot about this with energy and other important quantities that we'll talk about this semester. Okay, all right, moving along. So now this is going to be a little crash course into statistical mechanics. So the main topic of this semester is, as you know, thermodynamics. But I really think it's important for us to have a little bit of an introduction into the stat mech world, the statistical mechanics world. Statistical mechanics takes the world of quantum mechanics and combines it with the world of thermodynamics to look at how bulk and molecular properties evolve, or to look at how bulk properties evolve from molecular properties. Okay? So very much tied into that extensive versus intensive property. Okay, so here I have 4 boxes. And these 4 boxes are what I like to call the 4 things that molecules and atoms can do. They can translate, so that means they can move around. They can rotate, like that. So they can vibrate about a chemical bond, right? 2 nuclei can vibrate in and out of each other. And they can do electronic stuff. That electronic stuff is what we know as chemistry. Okay, so I want us to think of these boxes as energy. And in these boxes, I'm going to put a certain amount, or I'm going to talk about how much energy we can get out of these things. And I think maybe I can make some, can I make a thicker line? No, okay, that's fine. So let's see here. So the first thing that I'm going to do is draw a line right here, okay? And I'm going to call that level number 1. That's the ground state. Then I'm going to draw another line up here. That is level number 2. That is the first excited state. And then I'm going to keep going. I'm going to draw another level here, level 3, level 4, level 5, and so forth. And you'll notice what I'm doing here. I'm drawing these levels tighter and tighter and tighter. As it turns out, these electronic levels go up by 1 over the square. And we'll get into that in more detail in Chem 362. But what I want to point out, for a typical molecule or atom, this is just typical, right? So we live at the ground state. That's where we expect all things to be. But if we put some energy into the system, and exactly the energy we need, we can get it to level 2. Okay, hopefully you remember that from your Gen Chem days. And now, obviously, each molecule and atom will have different energy spacings. It's what makes them unique. It gives them the fingerprint. However, what is typical, the value of energy needed to undergo this transition, I'm going to write that down here, that is roughly about 1 to 10 electron volts for that first level. So that's general, right? And that's a big range. We noted that 1 electron volt was about 10 minus 19 joules. So 10 electron volt is about 10 minus 18 joules. And that's joule per 1 single molecule. But what if I wanted to talk about joules per mole? And even more appropriate units that we use would be the kilojoule per mole. Well, this same quantity of energy, this 1 to 10 electron volts, is about 1,000. Here we go. Oops, undo. Is about 1,000 kilojoules per mole. So I'm sorry, that got real sloppy here. I think that I have an eraser somewhere. Okay. Oh, there we go. Okay, now I'm just going to undo that. All right, here we go. So it's roughly, we'll just say 1,000 kilojoules per mole. All right? And obviously there's a range, but that's a good target area. It takes about 1,000 kilojoules per mole to get a molecule, or to get a mole of molecules, about 1,000 kilojoules, to go from the ground state to the second excited state. Okay. So now, if I were to zoom in on this level, right? So suppose I just zoom in way on this level. Just zooming in on that one level would give me the entire energy scale of this vibrational box, okay? And so I can put some energy levels in this vibrational box. And as it turns out, what we'll discover more in 362 is these levels are evenly spaced. I know I'm not drawing them evenly spaced, but you'll have to pretend. So level 1, 2, 3, 4, 5, 6, etc. They're all evenly spaced, okay? And once again, we expect all molecules in the vibrational level to exist at their ground state, and I'll talk about why that is, okay? So the requisite energy for a typical vibration, not all, but for a typical vibration, is just a fraction of that electronic level. It's about 0.1 to 1 electron volt for a typical spacing in a vibrational energy level. So about 10 times less than the electronic levels. Okay, and in terms of kilojoules per mole, that's roughly 10 to 100 kilojoules per mole for a collection of a mole of atoms. Okay, and similarly, if I were to zoom in on this level 1 in the vibrational box, we would find a whole bunch of underlying rotational energy levels. Okay, and so our rotational energy levels start off close together and then spread out. Okay, level 1, level 2, level 3, level 4, and so on and so forth, all the way up. Okay, lots. As it turns out, there's dozens and dozens of rotational levels, more than I care to draw on this picture. All right. And a typical spacing here are what I'm going to call milli-electron volt. So the milli-electron volt, that's 1/1000th of an electron volt. Okay, so that's about 10 to the minus 23 joules. So that's getting to be on equivalent with the value of Boltzmann's constant. Okay, and in terms of a collection of these molecules, that's about 10 joules, not kilojoules, but just 10 joules per mole. Okay, and now if I were to zoom in on any of these levels, I would find the translations. And there's no way I can draw enough lines for these translations, so I'm just going to try to color this in, right? There are so many levels in this translational box that they form what we call the continuum. Okay, that says continuum. So it makes a continuous stream of energy levels. So really, our rotational, vibrational, and electronic are what we call the quantized energy levels, because we have to have exactly the requisite amount of energy to go from one level to the next. If we don't have that amount of energy, if let's say we only have 85% of that energy, it ain't going to happen. However, with the translational energies, because these energies are so finely spaced together, it's kind of like the convergence of the quantum world to the classical world. So now in these translations, even though we can kind of loosely think of them as energy levels, molecules are really free to have like this continuous translational energy. They're not having to go through this quantized scaling up of energy. Okay? So those are the 4 things molecules can do. I want you to be very well versed and familiar with the 4 things molecules can do, because we're going to live, eat, and breathe and die by the 4 things that molecules can do. And I literally mean that. We are a result. The entire universe as we know it is a result of these 4 things. Pretty incredible, in my opinion. Okay, let's keep moving forward. So let's talk about the Boltzmann distribution. I'm going to write that equation down right here. So the Boltzmann distribution goes as n sub I divided by n sub j equals, I'm going to write exp. And when I write exp, I am talking about natural number e, the inverse of the natural log, just so that we're not confused between fundamental charge e and natural constant e. So this is 2.71 something or other, right? And when I put these in brackets, that means this is all e raised to the power. So I'll do a little code here. If I say like exp2, what I'm referring to is e raised to the power 2, okay? So this is now the exponential of negative, and then this is the quantity e sub I minus e sub j, negative of all of this, all divided by k Boltzmann times T. Okay? And if you think about your unit analysis, k Boltzmann was joule per Kelvin. So a joule per Kelvin times a Kelvin is a joule, right? Let's never forget the dimensional analysis. So that's energy, so that's joules on top. K Boltzmann is a joule per Kelvin times a Kelvin. So this is just unitless, right? And for something to be in an exponential, it has to be unitless. Okay? So now what does all this say? Well, N is the population of molecules in state I. That can be the ground state, it can be the second state, it can be the 4 millionth state. It's just a general placeholder. So Ni is the number of molecules in state I that have energy sub I. Nj is the number of molecules in state J that have energy sub J. And so the ratio of these two states will give us the relative population of things. For example, let's say in the ground state compared to the next excited state. So this gives us a distribution or a population of what molecules have energy I or energy J or whatever we want. Okay? So let's consider a few postulates of the Boltzmann distribution. The higher the energy of a state, the lower its population. Okay, higher the energy of a state, so the higher up it is on the energy scale, the lower its population is going to be. The higher the temperature of a state, the lower its population. Okay? So similarly, if I take a system that has a high energy state populated, but I cool it down, molecules will come back down into the ground state. It will be less populated in the excited state as I cool something down. And more states are populated if those states are closer together, if there's a smaller energy gap. So let's take a look at a random fictitious set of states. We could think of these as perhaps maybe vibrational energy levels if you want. Okay, and if let's say we can cool these molecules down to exactly 0 Kelvin. If we can get them to exactly 0 Kelvin, then by definition, I'm just going to like highlight this thing, color it in. Every single molecule, every single one will be in the ground state. There will be not a single molecule found in a higher lying state, including the translations. Okay? So what if I heat something up to room temperature? Same molecule, same energy levels, but now I heat it up to room temperature. Well, I'm going to be giving this molecule thermal energy. I'm going to be giving it thermal energy so that it can populate higher states. All right, so perhaps now only a fraction of those molecules are in the ground state. Some might even be in the first excited state, and some might even be in that third excited state. So it's going to make a distribution of states given to us by Boltzmann. And even though this could never happen, if we could get something up to like infinite Kelvin, then technically we would be populating like all of these states with equal probability, which just won't happen, okay? But if I heat this up from like 298 Kelvin to let's say 1000 Kelvin, I will see more of these upper lying states becoming populated. This is true for the electronic levels, the vibrational levels, the rotational levels, and the translational levels. So now we can kind of start to get a glimpse when we talk about molecules moving faster as a result of them getting heated up. It's because we're promoting those upper lying translational energy levels and those upper lying rotational energy levels as well. Okay. And if we heat something to the point where it glows, like think about if you have an electric stove. You crank that sucker, it's glowing red hot. That's because you've gotten it so hot that now the electronic levels are becoming populated. And to release that energy, they're crashing back down and releasing light as a result. Okay. So let's keep going on. I'm going to do just maybe a couple more slides for this first lecture. So now we can kind of get an idea of what these 4 molecular modes of motion look like and what kind of populations that they have. And so I'm going to talk specifically at 298K now, and still more generally like a general molecule. But as we can see, this is true for almost all molecules at room temperature. At 298K, this is the critical piece here. Okay, so we expect at room temperature, all molecules, all of them, will be in the ground electronic state. There's just not enough thermal energy at 298K to populate upper lying electronic states. There's just not, and we're going to calculate that soon. As it turns out, even with the vibrations, 99.9999999% will be in the ground vibrational level. So perhaps a very, very small fraction will be in the vibrational level. Even so, we expect at 298K, all molecules will be in their ground vibrational state. Now, as it turns out, there's a distribution in the rotational levels. And that's because the levels are very finely packed together. So that was one of those postulates, right? The finer the levels are together, the closer they are together, the more of the upper lying states will be populated. So what we will actually see is an actual distribution. Hopefully these little scribbles I'm doing make sense. If I scribble all the way over, that means the level is completely populated. So the rotational levels will actually have like some kind of distribution where there will be some peak energy level, maybe 1, 2, 3, 4. Perhaps the 4th level of the rotations will be the most populated level. Okay. And then with the translations, we also expect some type of distribution, right, where there is going to be some maximum populated state, which would correspond to like the most probable speed that the molecule's traveling. And we're gonna take these kind of sloppy diagrams that I'm making and turn these into actual graphs of the distribution of populations of states. Okay. And so now this gets us to the equipartition theorem. And this is another set of conceptual information I want you to know. And the equipartition theorem says, in a sample of temperature T, all quadratic contributions to the total energy have the same mean value, which is 1/2 times the quantity K Boltzmann times the temperature of the system. Okay, so I'll say this again. In a sample of temperature T, whatever the temperature is, T for the generic temperature, all quadratic contributions, so, right, something raised to the square. Whatever that parameter is, we'll see what that parameter, that quadratic is. All quadratic contributions to the total energy have the same mean value, which is 1/2 times Boltzmann's constant times temperature. Okay, this is a rather obscure theorem, but we're going to prove in several different ways this week and next that this theorem is a damn good one. Okay, so let's move on, and I'm going to give you another activity to work on. And I want you to read through this, and I want you to really use your brain power from that equipartition theorem to see if you can come up with an equation for the kinetic energy of a noble gas as a function of temperature. And I say noble gas just because we're talking about a perfect atom. A perfect atom, it's not going to vibrate. It has no bonds to vibrate against. And when it rotates, as we'll learn later, it has no moment of inertia because it's just an atom. So we're not worried about its rotation. So the only thing we're worried about with this is really like thinking about the translations. And we can also think about the electronic transitions. But for now, just kind of think about how we calculate the energy of an object in kinetic motion. So that's your hint. Okay, so think through these things, pause it if you want, or I'm going to play a little bit of music and you can kind of follow along. Okay?
All the kids say they love it, wanna make it love. Welcome to the world of the plastic beach. Yeah. Welcome to the world of the plastic beach. Welcome to the world of the plastic beach. Yeah. Welcome to the world of the plastic beach. Welcome to the world of the plastic beach.
Okay, so this is kind of an obscure, asking you to kind of think through this. But if we think about a molecule, or in this case, just a noble gas, right? Translating around, it's free to move in the x direction. And for a gas, the plus x will be the same as the minus x, right? There will be no difference between those dimensions. As we shall see in liquids and solids, movement in the positive x direction and movement in the negative x direction is significant because liquids and solids are compact together. They might have a neighbor that's different in the negative direction as the positive direction. But for gases, there's only 3 of these contributions, x, y, z, because of the way that it can move around and it's not close to any other neighbors. Okay, so if we know each quadratic contribution contributes 1/2 kBt, we have 3 of them, then the kinetic energy of all atoms is 3/2 k Boltzmann T for a single atom, or 3/2 RT for a molecule, or 3/2 RT for, a mole of atoms. Okay, so 3/2 kBt is the kinetic energy. Maybe you remember that equation from Chem 109. This is where it comes from. It comes from the equipartition theorem. Okay, so if we go ahead and calculate that, right, we know the value of Boltzmann's constant is 1.38, 2 sig figs is perfectly fine, times 10 minus 23 joule per Kelvin. And I think I asked you to calculate this at room temperature. So then times 298 Kelvin, and I get 6.2. I'm going to take away another sig fig because this is really just for approximate. 6.2 times 10 minus 21 joules is the average kinetic energy of a noble gas at 298 K. So that's not particularly a useful number. So make sure that you can do this. I'm just going to write the results down. But if I wanted to convert this into electron volts, this would be 38.7 milli electron volt. Practice it. Make sure that you can arrive at that number. And this would also be 3.7 kilojoules per mole. Okay? So now the question is, I think that I asked, let me go back to that slide. How does this compare to the quantized modes? Let's see, do I have, nope, not the next slide. So how does that compare to the quantized modes? 3.7 kilojoules per mole. So let's back up for a second. And we talked about, I'm going to write that number down, okay? 3.7 kilojoules per mole. So what does that number mean? What that number means is at 298 Kelvin, a noble gas, and we'll talk about how to scale that up for molecules and such, but a noble gas has 3.7 kilojoules per mole of available thermal energy. So, does it have enough energy to self-promote to an upper electronic level? Absolutely not. It needs about 1,000 kilojoules per mole. This is why at room temperature, everything is in the ground state. Practically everything, okay? Well, what about the vibrational levels, okay? Well, you need about 10 to 100 kilojoules per mole, and that's a range, right? But even so, 3.7 kilojoules per mole is not enough energy to be into an elevated vibrational level, even though technically it's a noble gas and it doesn't have a bond to vibrate on. But if we had a similar molecule with that kinetic energy, 3.7 kilojoule per mole, it has to exist in the ground vibrational state. It does not have enough thermal energy, thermal kinetic energy, to self-promote to an upper lying vibrational level. Now, the rotational levels are only spread out by single millielectron volts, which is like 10 joules per mole. So we have more than enough thermal energy at room temperature to have a series of populated rotational levels. And that's true for atoms and that's true for molecules, okay? And then the continuum, these energy levels are crazy small together, sub-millielectron volt. So this is why, if I move forward a little bit here, this is why we see at 298 K, at this temperature, there will be a population of translational levels. There will be, some maximum population level, and it's going to have a distribution. It's actually going to be shaped like some type of curve. It's not a bell curve, it's a Boltzmann's curve, and we're going to explore that more soon. The rotational levels are also going to have some population of states. Okay, so when I say population of states, this is really what I'm referring to. However, the vibrational levels, 99.99999% of everything will be in the ground state. And with the electronic levels, 99.999999999% of everything will be in the ground state. Okay, so hopefully connecting, I'm going to end this lecture now. Big take-home message. Everything is in the ground state at room temperature for the electronic levels. Practically everything is in the ground state at room temperature for the vibrational levels. And the rotations and the translations have a population of states due to the available thermal energy. And as we shall see, because of those populations of states and the rotations and the translations, that energy can be harnessed. It can be used to do stuff. It can be used to transfer energy to other molecules upon collision. It can be used to convert into potential energy. So this is all kinetic that we're talking about, okay? So these are really reservoirs of thermal energy. Thermal energy can't just exist. It has to go into these molecular modes of motion. And at room temperature, the translations and the rotations represent a reservoir for this available thermal energy. All right, folks, that's pretty good for day one, week one, first lecture. Feeling great. Hope you're feeling great too. And I'll see you at the next one. Peace.